Okay, first off, these things should be reviewed. Things came up with words that kind of worked is the base. Thinking about exponential exponent. One, that's how we know that the function increases. And we're going to get that kind of shape for the exponential graph. Okay, so that's what an increasing exponential graph looks like. When b is between 0 and 1, okay, it's going to be decreasing, and it's going to have that sort of shape there. Right? So we didn't talk about any of that first semester. Again, that's more review back from what you had known from previous classes. And we're using these words because this unit is mostly logs. Okay, we start with exponentials because they're inverses of logs, but we're going to transition to logs by Friday. So Friday will be the first day that you actually start working with some logs. Now, I had us review the transformations because this is how we're going to go about graphing these exponential functions. So let's just start off with the names. When the value is added after the function operation being the actual exponent, that is a vertical shift. Okay, and when it's positive, we're going to shift the graph up by c units. When it's negative, we're shifting it down by c units. Okay, and I feel like those are two that we should kind of have an idea of without me giving you anything. Then, when c is being added onto the x or subtracted from the x, that's our horizontal shift. And remember, that one can be tricky because it's the opposite operation from what we see. If it's x plus c, we're actually shifting the graph left by c units. If it's x minus c, we're actually shifting it right by c units. Okay, so anytime it's affecting the x's, it's the opposite operation from what we see. I did add in parentheses here, more so to keep track of the order of operations. If the base itself is negative, the graph is really kind of funky. So it would have to be outside those parentheses there. So go ahead and add those in. Anytime we see these negatives, those are going to be reflections. So both those next two are reflections, the top one being a reflection about over the x-axis. Really what's happening there is we're multiplying all the y values by -1, and so it's taking all the points from above the x-axis, making the y's negative, and reflecting across the x-axis. When the x itself is negative, okay, the reflection is the opposite. So now there's going to be a reflection over the y-axis. So your last two are your stretches and compressions. With the top one, c times b to the power of x, is your vertical stretch or compression. Now, the one thing I want us to add in there is how we know whether it's a stretch or compression. And this is, again, directly taken from the transformation stuff we already know. When c is greater than 1, that's when we know it is a vertical stretch. When c is between 0 and 1, that's how we can tell it is a compression. When that value shows up in front of the x, that's our horizontal stretch or compression, and the rules are the opposite here. So if it's greater than 1, now it's a compression, and if it's between 0 and 1, now it is a stretch. Okay, and again, those are just reminders about transformations. And that's, as we graph these exponential functions, that's what we're going to use, is kind of the same transformations that we had done previously. Now, the last thing I want you to add in here is the order in which we apply transformations, because that's really important. Otherwise, it does not work out to be the correct graph. So we have to first apply any stretch, compressions, or reflections first. Okay, so when we start actually graphing these, make sure you do that part right away. Then, after you've done the stretch, compressions, or reflections, that's when you can go ahead and do your vertical and horizontal shifts. So keep this order in mind as we actually jump into the graphs for today. Okay. So we're going to talk about graphing. Since you only have 2 pages per group, maybe you kind of rotate who's writing and working through the graphs. Basically, how we're going to do this, I'm going to do the first 2 for us. You're going to do the next 2, and the last 2 we're going to do all together. And that should take us to the end of class. Now, for the most part, we're going to try to just simply apply transformations like what we just kind of talked about. Know that when in doubt, if you ever asked to graph a function and you don't remember, simply plug in x values and see what y's you get and just plot the points. Okay, that 100% of the time works. And you've heard me say that over and over again. Okay, so even if after today you're like, I do not remember how to apply transformations, plug in values for x and see what y values you get and plot them that way. Okay, always works. Now what we're going to do is we're going to start by plotting the parent function. Then using that parent function, we're going to apply the transformations to the parent function. So I've kind of set it up to where the graph on the left is the parent function and the graph on the right is going to be the transformed function. So let's first just make note that this is our parent function. And so we're going to come up with points for this parent function by actually plugging in values for x. And this is a good reminder for how we deal with exponents, especially negative exponents. A lot of us forget about that. So we're going to pick some x values, and we're going to find the y's. And for this, let's do -2, -1, 0, 1, and 2. Okay, and we're going to fit as many points as we can on this graph. So when I have 2 to the power of -2, remember that negative exponent is really flipping the base. So instead of the base being 2, now it's 1/2, and then this is raised to the power of 2. So it's really 1 over 2 squared, which is 1/4. Okay, so negative exponents don't make the value negative, rather they just flip the base. And so they're making that value smaller and smaller and closer to 0. Okay, so similarly, 2 to the power of -1/2 is 1 over 2 to the power of 1, which is just simply 1/2. Anything to the power of 0 is 1 itself. And then the positive exponents we usually don't have much issue with. So that'd be 2 to the power of 1 is 2, 2 squared is 4. And you know, I think we can actually get a value that fits on our graph for 3. 2 to the power of 3 is 8. So we're going to go ahead and plot all of these points. So -2 1/4, -1 1/2, 0 1, 1 2, 2 4, and 3 8. This is the graph of our parent function. Okay, I should be able to look at the equation, know that it is increasing because of the base being greater than 1. I'm seeing that in the actual graph and that the values are going up as I work my way to the right. And so the last thing I want to point out here, and a really important feature of all exponential functions, is the horizontal asymptote that is a part of every exponential graph. Okay, those are really important for us to identify. And the reason they show up is because if you think about values that we plug in as exponents, right? As I make the exponent more negative, that value is just getting smaller and smaller and smaller, but it's never getting negative, right? If you look at just these negative exponents here, it's 1/2, 1/4, the next one would be 1/8, 1/16, and so forth. So it's getting really, really, really close to 0, but won't actually ever get all the way there. Hence, creating a horizontal asymptote where our graph's going to get really close to it, but won't actually touch it or cross it. Okay, so that line should always show up when you're graphing exponential functions. So the last thing we're going to do with all these graphs is describe the domain. I can see the graph is going all the way left to -infinity and all the way right to +infinity. And I can also think about that in terms of what values can be exponents, right? Any value can be an exponent. -1000 is a valid exponent. +1000 is a valid exponent. Okay, so every value of x can be used here. Now the range, however, is related to that horizontal asymptote. Because I can't plug in any value of x and make the whole thing negative, the lowest it's going to get to is 0. Now we're using a curved bracket there because we're not going to get all the way to 0, but we'll get really, really close. Okay, the smallest decimal that you can think of is as close as we're going to get to that line. Okay, so it's 0 with an open bracket, and it goes all the way up to +infinity. Then the asymptote, okay, that is a horizontal line where on a horizontal line, it's the y coordinate that's always staying the same. So in this case, y is staying the same at 0. So the equation of our line is y equals 0. All right, so here's how we're going to graph transformed functions. We're actually going to copy down the parent function. Even though we have it over here, you are going to get an assignment where there isn't a place for you to graph the parent graph. So we're going to do that on the same graph itself. So I'm going to plot this parent function, just the same thing I had before. So 2, 4, or 1, 2, 2, 4, and 3, 8. The only thing I'm not going to add into the parent function is the asymptote. I'm only going to add in the asymptote for the transformed function. Okay, so using this parent function, I'm going to apply the transformations directly to it. So in these transformations, I want to identify what is going on with all these transformations. Well, the only thing that's happening here is we're shifting everything down 3. And so I can literally go to every point and just simply move it down 3. And that's a really easy thing to do on the graph. So this y-intercept, I'm going to go down 1, 2, 3. That's our new y-intercept. Take this point down 1, 2, 3. Down 1, 2, 3. Down 1, 2, 3. And then this last ones that are fractions, that's a half. So 1, 2, 3. This is the quarter, 1, 2, 3. Okay, and then also, even though we didn't add in the asymptote, that also gets shifted. So it's going from 0 and it's getting shifted down 3. And hence, the vertical shift is always going to be where your horizontal asymptote lies. So the horizontal asymptote lies at -3. And there's our transformed function. Okay, so that is the same process what we were doing back with transformations when we were applying to like doing values with the points. Now we're just doing it on the graph. We're not having to do any addition or subtraction. We're just literally counting down 3. If we had a horizontal shift, we'd count how far left or right. So our domain here is -infinity to +infinity. The range, the lowest it gets to is -3. It goes up to +infinity. And then the asymptote is the value of the vertical shift, which is -3. So y equals -3. All right, I'm going to give you, let's say 5 minutes to do graphs 3 and 4 on the other side, and then we're going to do 5 and 6 all together. Work in your groups, whether that be a partner in your group or all together, does not matter to me. Let's go over 3 and 4 here. Again, the negative exponents with so my values are going to get bigger as the x values are negative. Take it to b, take it to the power, that's why it's 27. Okay, 1/3 of the power of -2 is equal to 3 squared, which is 9. 1/3 of the power of -1 is 3 to the power of 1, which is 3. Okay, so we're getting our values to grow as we work our way to the left here. Still, anything to the power of 0 is 1, and then our fractions show up to the right there. Domain, range, all the same with our horizontal asymptote. So now, when we go to apply the transformations, I would look at the equation, and again, I'm just copying over the parent function, and I'm recognizing that I'm shifting everything right 2 and then up 1. And again, the order in which you do that doesn't matter. So all I'm doing is finding a point from my parent function, counting right 2 and up 1. And there's my new point. Same with the next point, right 2, up 1, right 2, and up 1. Okay. I didn't even worry about the fractions because we start to see those fractions as they get into that kind of tail or area towards the horizontal asymptote. So I'm not even adding in the 1, 1/3, 2, 1, 9. Right? Any questions here? with how I came up with anything or how I'm doing the transformations? Okay, so I want to do this last one together. We'll see how far we can get. The reason I want to do it together is because this one has a reflection and also a stretch. And so we're actually going to want to do this in multiple steps. So the first thing is, let's graph the parent function. We'll do that pretty quick. So x and f of x. So we'll go negative, we'll just do negative 1, 0, 1, 2, and 3. 3 to the negative 1 is equal to 1/3 to the power of 1, which is just 1/3. Any to the power of 0 is 1. 3 to the power of 1 is 3. 3 squared is 9. 3 cubed is 27. That point won't fit, but it doesn't hurt for me to at least jot that down. So I'm going to plot these. Negative 1 and 1/3. 0, 1. 1, 3. And 2, 9. Add in the asymptote as well. And our domain for all exponentials is negative to positive infinity. That won't change. The range is 0 to infinity. And the asymptote is at y equals 0. So now, let's copy over this parent function without the asymptote. So 0, 1, 1, 3, and then 2, 9. I'll go and throw in one of these fractions. And so since we have a vertical stretch and a reflection, that shows up here in this negative 2. Okay, this is a reflection and vertical stretch. That has to be applied first. So my recommendation here, when we go ahead and do this, is to actually graph that function with the vertical stretch and reflection before we do any shifting of left or right. So I'm going to actually graph y equals negative 2 and then 3 to the power of x next. And so I have to think back to our lesson on transformations. What does a vertical stretch do to the values? It multiplies all the y's by that value. So instead of this being at 0, 1, that y value gets multiplied by negative 2, reflecting it across the x-axis and stretching it out to be down at negative 2. This y value here at 3 is going to get multiplied by negative 2, moving it down to negative 6. This one here at at 9 is going to get multiplied by 2, bringing it to negative 18, which isn't going to fit on our graph. Okay, so maybe we get one more point from the tail. Even though I didn't plot those, this negative 1, 1/3 is going to go down to negative 2/3. Okay, and so that is our reflected and stretched out graph. And so then, to complete this graph, we'll add in the last two transformations. Which is shifting everything right 1 and up 2. And this will actually be what we'll lead with when you all come in tomorrow, since we are in our last 30 seconds. All right? Welcome back again. Hope the rest of your day goes well. And I'll see you all tomorrow. No, keep these. Bring them tomorrow. We're going to finish this. And then you're going to have an assignment doing this exact stuff.